By now we know how to find the volume of solids of revolution using both the disk and the washer method. What we're going to do in this video is move the axis of rotation off of the primary x and the primary y axis. And instead, we're going to rotate regions around arbitrary vertical or horizontal lines. The horizontal line y equals 5 could be an axis, or the vertical line x equals -2 could be an axis of rotation. So I'm going to go through a couple examples on how that works. The good news is that the formulas for disk and washer are going to be the same throughout. What's tricky here is just to remember that we always go right minus left or top minus bottom, and it's not going to be simply function to 0, function to 0. It might be function to -5 or function down to -10. And so we'll kind of see where these different axes of rotations exist. So here's an example. We have a region in quadrant 1 that's underneath the graph of 4 minus x squared. And there's a picture here of that region. I colored it in the region in blue. And it's going to be rotated around the vertical line x equals 3. So what I'd like you to do is label that vertical line x equals 3, kind of map that or sketch that out if you're making this graph on your own from scratch. Label your region, any maybe key ordered pairs, key intersection points like 0, 4, the y-intercept of that region. Down here, we're going to cross the x-axis at 2, 0, so just kind of the behavior of 4 minus x squared. And because we're rotating the region around a vertical line, x equals 3, we want to draw a horizontal slice, a representative rectangular strip in that region to represent sort of that part of the Riemann sum. And then as it spins around the axis of rotation, just always make sure for the disk and washer method that that strip you draw is going to be perpendicular to the axis of rotation. Now, I like to draw an arc wheel on the axis, and that arc wheel is provided for me right here. Just again, another visual reminder as far as where this region is spinning. And then with the new axis of rotation, I'm going to label that axis and put a rectangle around it. So x equals 3 is going to go on top of that dashed vertical line. I'm going to put a big rectangle around x equals 3. It's very clear on my image, on my picture, where the axis of rotation is and then where the region is with respect to it. And that's going to be important that you keep track of the picture and that your graph looks accurate, your region is sketched accurately so that we can find the correct radii for either the disk or the washer method. Now, this is going to be a washer problem. If you notice here, I have an outer radius kind of bracketed out in the diagram, and then an inner radius as well. So because the rectangle is horizontal, I'm going to have a right minus left situation. Let's begin with the inner radius, lowercase r, inner radius. I'm going to put my fingers on the paper, my right index finger down on the axis for the inner radius, the right side of the inner radius, and then my left finger will go on the left end of the inner radius. And so as I look at where I am on the paper, on the picture, right minus left, well, my right finger is on the line x equals 3, and my left finger is on the function. So the inner radius is changing according to the function. Now we're going to be building a y integral here. This is a dy thickness to that washer that we're about to build. And by the way, maybe jot this down on your paper. Always remember that the direction we go with the subtraction is always right minus left for horizontal distance and then always top minus bottom for vertical distance. So having said all that, let's begin by, actually, if we're going to build a y integral, we want to rewrite this function up here, y equals 4 minus x squared. Let's do a little bit of quick algebra and write that in terms of y. So how about we call this y, or how about x squared plus y equals 4. So x squared is going to be simply 4 minus y, and x is equal to the square root of 4 minus y. So there's my parabola piece, radical 4 minus y. So for right minus left, inner radius, we're going to have 3 minus the left, which is the function, and that's root 4 minus y. That large expression is the inner radius. Let's find the outer radius of this washer. The outer radius, again, a right minus left, 3 all the way over to what looks to be the y-axis. Well, that's going to be 3 minus 0. So my capital R, outer radius, right minus left, 3 minus 0. Now, you could simplify that and just say 3, which is okay, but I like students to see where the right end is and where the left end is, even if there's a 0 in there somewhere, just to keep track of the different dimensions of the washer radii. Now, find the volume of the solid. So our final step here is to use our washer formula. The volume by washers will be pi times the integral, and I want y-axis bounds, so that region is going to be integrated from 0 to 4 for the volume. And then I have capital R squared minus lowercase r squared. Outer radius squared minus the inner radius squared. And then dy at the end. And there it is. By the way, be careful that you don't, remember that capital R minus r, lowercase r, if all that squared does not equal r squared minus little r squared, so be careful with that little twist in algebra. Don't make that mistake when you're simplifying your integrals. At this point here, I would just ask you to take out your calculator and maybe compute pi as well. So if you want to pause the video and try this on your own, you can go ahead and do that. Type it in, pi, and then math 9, type in your integrand, press enter. Even though we have y's in here, you can replace those y's with x's on the calculator. Final answer should be 75.398, and that is a volume calculation, so the units would be units cubed. But again, in a generic setting like this, you would not be required to put down units. Okay, so again, just disk washer. This was a washer example, but the only difference is that the axis is not the x-axis or the y-axis as far as the rotation is concerned. Let's look at another example. How about the same region, y equals 4 minus x squared in quadrant number 1, only now we're going to rotate this region around the line y equals -5 to form a solid. And again, here's my arc wheel. There's the picture. I have an outer radius, inner radius situation. I'm going to label this y equals -5, put a big rectangular block around that axis of rotation, just so that you know where it's at. Include an arc wheel. There's an arc wheel provided here in the diagram for me, which is great. And because we're going to go around y equals -5, the sample rectangular strip is vertical. That means I have a dx thickness to it as I construct the washers from the rotation. The washers will have a thickness of dx. And I can now go back to the function of just being 4 minus x squared for the integral. But let's not get too far ahead of ourselves. Let's find the two radii. I want the inner radius, top minus bottom in this case. So the top of the inner radius is at 0. The bottom of it is down at -5. So again, top minus bottom is going to give me 0 minus -5 for the inner radius. Same thing for the outer radius. Now the top of the outer radius is changing according to the function. So the top would be 4 minus x squared. And the bottom is fixed, though. The bottom of that outer radius is going to be fixed on the axis of y equals -5. So top, 4 minus x squared, minus -5. And watch out for that double negative in that problem. So maybe we want to simplify that to say 0 plus 5. That would be just fine. 4 minus x squared plus 5. Maybe you want to say 9 minus x squared. That would be okay, too. We can make those little algebraic simplifications if you want to. You can combine like terms and just make your integral a little bit easier to write. So let's find the volume of this solid washers once again. So pi, the bounds will now be from 0 to 2 because I want x-axis bounds. And then I want capital R squared, outer radius squared. So 9 minus x squared, quantity squared, minus little r squared, or just 5 squared, and then dx thickness. There's the integral. Go ahead and pause the video, give it a try, type in pi, and then math 9. Let's see if we can get the answer here. Solution should be 221.168 units cubed for the volume of that solid of revolution. As always with calculators, don't forget to round to 3 decimal places. So I thought I could end with one final example for you. And here's one region, a different region. It says this region R is bounded by the quadratic 2x squared, the parabola 2x squared, the horizontal line y equals 0, and then the vertical line x equals 2. So I have that picture kind of graph right in here. But let's actually try to take that very same region and go around the line y equals 8. So again, stop the video, give it a try, see if you can figure out how this setup would work. Okay, here's the region. And if I want to rotate this around the line y equals 8, I'll graph the axis of rotation, label it y equals 8, put a big rectangular block, and then an arc wheel to show the rotation taking place. I need a vertical rectangular strip. I'll put that right in there. dx thickness. It's going to be a washer problem. Let's find the outer radius and the inner radius. Here's capital R, and then up here would be lowercase r. So the volume, the bounds would be, let's see, x-axis bounds. That'll be from 0 to 2. And then I want capital R squared, top minus bottom, looks like 8 minus 0, minus inner radius, again, top minus bottom, appears to be the function 2x squared minus 0. Let's see here. Sorry about that. Top minus bottom of inner radius would be 8. The top of it is 8, and then minus function, I should say. So 8 is the top, and then minus the function. There we go, and then dx thickness, and then we're on our way. Calculator time, type in pi, type in math9, and then you can compute that integral to find your solution for the volume. And that volume would be 187.658 units cubed. So that's basically how we use disks and washers to find the volume of solids of revolution if the axis of rotation is off the x and the y axis. Now we know how to find these volumes if we rotate these regions around any vertical or any horizontal axis on the coordinate plane. If you have any questions, feel free to reach out, but I hope this video and these examples were helpful for you. So good luck with your integration and with finding your volume.